This is section 5.3, Rules for Definite Integrals. You'll find these rules on page 269 in your textbook. The first rule is, rule number 1 is called order of integration. And what it says, if you have an integral, this is for rule number 1, that goes from b to a, f of x dx. If you want to switch the boundaries, for example, if maybe you notice that the smallest number is on the top instead of the bottom, and you want to switch those upper and lower bounds around, you can do that as long as you change the sign out front. Okay? So for example, let's say that the integral from 1 to 3 of some function f of x dx equals negative 5. So then, the integral from 3 to 1, if I switch the bounds of that same function, dx, would equal what? Positive 5, yep. If you switch the bounds, then the answer just changes signs. By switching the 1 and the 3, the negative 5 answer now switches to positive 5. Okay? So that's a rule you can always switch those bounds as long as you switch the sign on the answer. Rule number 2 is called the zero rule. If you're taking an integral from a to a, f of x dx, that answer is going to be 0. So here's my example. Let's say you're doing the integral of x squared from 4 to 4 dx. What's that answer going to be? 0. Here's the reasoning behind it, at least one way you can reason it out. If you graphed y equals x squared, and then found the area between 4 and 4, how much area is there between 4 and 4? None. Okay? If your left and right bound are the same number, there's no area on the line. There's no area in there. Okay? You're not going between 0 and 4, you're going between 4 and 4. There's no area between 4 and 4. So that's the reason the answer is 0. Any questions about that? Anytime you notice the upper and lower bounds matching, the answer is going to be 0. Third one is called a constant multiple. It says that if you have an integral from a to b of k, so k is some constant, times some function f of x dx, that basically what you can do is move that constant out front. You can put the constant out front, then evaluate the integral. So for example, maybe you're trying to take an integral from 0 to 1 of 1/2 x dx. What you could do is move that half out front, then take the integral of x dx from 0 to 1 still. Get this answer, which let's go ahead and do that. To get that answer, I'm going to use a graph here. I'm going to graph y equal x. So y equal x is the diagonal like that, right? From 0 to 1. So the area of that little triangle would be the value of the integral from 0 to 1. What would be the area of that triangle? This is the point 1, 1 right there. That'd be a half, because it's 1 times 1 divided by 2 would be a half. So the integral part of this would equal a half. And then you also have to multiply by the half out front. So your answer is going to end up being a half times a half. So the integral is actually going to equal 1/4 in this case. So sometimes it helps to move your constant out to the front and just kind of ignore it until after you've found your integral value, then multiply by that constant later. Makes your calculations a lot easier sometimes. Any questions about that one? Okay, number 4, sum and difference. This is basically saying that if you have addition or subtraction, that you can separate those integrals. You can separate an integral into more than one integral. I'm just going to show an example here. Let's say I have the integral of something like let's say we go from 2 to 5 of x squared minus 3x plus 1. And that's all quantity dx times dx. this rule says that what you can do is split these up into three separate integrals. You can split it up as the integral from 2 to 5 of x squared dx minus the integral of 3x from 2 to 5 dx plus the integral of 1 from 2 to 5 dx. So it's basically just splitting up the polynomial here into three separate parts and taking the integral of each piece. Sometimes that makes the problem simpler if you can integrate each piece individually and then at the end just add or subtract all your answers together.
Can you do that with multiplication too? Or just
You cannot do it with multiplication. Very good question. You can only do it with addition and subtraction. Okay? Next, rule 5. Looks a little bit different. Let me grab another piece, another transparency here. Rule 5 is called additivity. And doing the integral from a to b, f of x dx, plus the integral from b to c, f of x dx, is going to equal the integral from a to c, f of x dx. Let me draw you a picture to explain this. Let's say we have a, b, and c. So we have some type of function here. The integral from a to b would be this area right here. So this integral would be represented by this area. From b to c, this integral would be represented by this area, this polka dotted area here. So if you add those two areas together, what do you get? Integral from a to c. You get this final. So that's all they're saying is if you add the first area plus the second area, you get the total area. So let me give you an example. Well, let's move on. I think we'll come back with some examples in the assignments later. Any questions about that one? All right, flip to the back side. Min-max inequality on the back of your paper. If max little f and min of little f are the maximum and minimum values of f on AB, then min of f times b minus a is less than or equal to the integral, which is less than or equal to the max of f times b minus a. So let me try to show you a picture of this to help explain it. Here's the rule again. The minimum of f, whoops, not myth. Min of f times b minus a is less than or equal to your integral from a to b of f of x dx, which is less than or equal to the max of f times b minus a. Picture's going to look something like this. Let's say my f of x curve looks something like this. Let's say a is right here. Let's say b is over here. It's my f of x or y-axis. This is my x-axis. All right, first of all, what area is represented by the integral? Integral represents what area? Right in here, right? This area here? Integral right here represents that area. See if I have a different color here. The min of f. Well, the minimum of f would be the lowest point on the curve, right here. So the min of f would be about right there. How about b minus a? What's b minus a on the picture? If this is b and this is a, what's b minus a?
The
Distance between them, yeah. So this distance right here is b minus a. This height, let me draw my line all the way across. And I'm going to put some stripes in this box right in here. How would you find the area of that rectangle? What would you multiply? Yeah. You take the min of f, that would be the height, times b minus a, that would be the width, and that would give you the area of the small rectangle. So that's what this left piece here represents, is the area of the smaller rectangle. I'm going to have two rectangles here in a minute. Area of the small rectangle. The max of f. Well, the max of f looks like would be about right here at the right endpoint. Would be the max of f. So now look at this big rectangle. This entire big rectangle here. How would you find the area of that big rectangle? Max of f times b minus a. Yep, the max of f would give you the height. B minus a would give you the width. So that's what we have over here on the right. The max of f is the height of your rectangle. B minus a is the width. When you multiply them, you get the area of the rectangle. So this is the area of the large rectangle. Okay? So would you agree that the integral, the area under the curve, between the curve and the x-axis, is somewhere between the small rectangles area and the big rectangles area? Do you see that? That integral is going to be somewhere between those two areas. Any questions about that? Okay, number 7. Let me grab a new sheet for this one, I think. I need to look at these transparencies and I'm done, I know. But number 7. It says, if f of x is greater than or equal to g of x on an interval a to b, that tells us that, or that implies that the integral of f of x dx from a to b will be greater than or equal to the integral of g of x dx from a to b. This might look complicated, but it's really not. Let me show you a picture. F of x being greater than or equal to g of x. That means the f of x curve is above the g of x curve, or it could touch the g of x curve, but it cannot go below the g of x curve between a and b. So let's say this is a, let's say this is b. This is telling us that our f of x curve is going to be above our g of x curve. This is our g of x curve in black. I'll draw a couple lines in here. So this first part is telling me the f of x curve is either going to be greater than or equal to the g of x curve. Higher on the graph, in other words. Or it could come down and touch, but the blue line could not go below the black line. The bottom part is saying then the integral of f of x dx, which would be this whole area here, has to be greater than or equal to the integral of g of x, which would be this area here. Which is kind of obvious, isn't it, that the blue area is going to be greater than the black area? So really, if they're stating something that's really obvious when you draw a picture, if the f of x curve is above the g of x curve, then there's going to be more area under the f of x curve than there will be under the g of x curve. That's all that's really saying. Any questions about that? All right, let's get started on assignment 5.3 next. Out of the book.